Hi everyone, we're going to go ahead and get started. I'm Emma Brunskill. I'm delighted to welcome you to Reinforcement Learning CS234. This is a brief overview of the class and what we're going to be covering today. And I just want to start that probably everyone's heard of reinforcement learning these days. That wasn't true about 10, 15 years ago. But you can describe what is happening in reinforcement learning by a pretty simple statement, which is the idea of an automated agent learning through experience to make good decisions. Now, that's a pretty simple statement to say. It sort of encapsulates a lot of what me and my lab and many, many others have been trying to work on for the last 10 to 15 years. But it's sort of deceptively simple because it involves a lot of different really challenging and important things. So the first is that any sort of general agenda to try to achieve general artificial intelligence has to include the ability to make decisions. There's been absolutely enormous progress in what we would call sort of perceptual machine learning, things like being able to perceive faces or cats or like identify cars. And we call that often perceptual machine learning because it focuses on trying to, say, identify something. But of course, in reality, what we're all trying to do all the time is also to make decisions based on our perception and based on our information we're receiving. And so it's critical if we think about what it means to be intelligent to consider how to make decisions, and not just any decisions, but what it means to have good decisions. This sort of question over how can we learn to make decisions, particularly faced by uncertainty and limited data, has been a central question that people have been thinking about at least since the 1950s, particularly pioneered by the ideas of Richard Bellman. And we'll hear a lot more about Bellman's equation, which many of you might have seen before, later even in this lecture or next lecture. So there's one sort of argument for studying reinforcement learning, which is it's an essential part of intelligence. It has to be part of a general agenda of artificial intelligence. And so we should study it to try to understand what it means to be intelligent. And that certainly for me is one of the really big motivations, is that I think there's just a lot of fundamental questions about what is the data needed to learn to make good decisions. But there's another really good motivation to study reinforcement learning, which is that it's practical and it allows us to solve problems we'd like to solve. So in particular, over the last roughly decade, there's started to be a lot of really impressive successes of using reinforcement learning to tackle problems or to get unprecedented performance in a lot of really important domains. So the first one is the board game Go. So who here plays Go? Okay, a few people, maybe not. You can talk to the people that raise their hands. So it's an incredibly popular board game. It's also an incredibly hard board game. It's far harder than chess, and it was considered a really long outstanding question of artificial intelligence. But roughly I guess about 8 years ago now, 8 to 9 years ago, there was a team at DeepMind, which was still a fairly small organization at that point, that thought that they could make significant headway at teaching AI agents to be able to play Go. And the idea in this case is that we're going to combine between the ideas of reinforcement learning and Monte Carlo tree search, which is something we're going to hear about later in this class, to create a system that played Go better than any humans in the world. And so there's even a movie now about sort of one of the seminal games in that sort of endeavor and how humans felt about that and how the creators of the AI systems felt about that. But this feat was achieved far earlier than what people expected. And one of the key reasons for that was using reinforcement learning. Another really interesting place that we've seen progress of using reinforcement learning to tackle incredible challenges is in the idea of fusion science. Fusion is a potential approach for trying to tackle the huge energy issues that we have and trying to transition to more sustainable options for that. And one of the challenges here, and I'm not a fusion expert, is to manipulate and sort of control things within a vessel. And so what the reinforcement learning question in this case is how do you command the controllers, the coil controllers, in order to manipulate this into different types of shapes? And so this was a Nature paper from 2 years ago where they showed you could use deep reinforcement learning techniques to accomplish this in a way that was far more flexible than had previously been imagined. One of my favorite examples of the applications of reinforcement learning comes from a pretty recent important case, which is COVID testing. So this was a system that was deployed in Greece. They had limited resources, and they were trying to understand who you should test in order to help control the epidemic. because as many of you may know, there's a lot of sort of free movement within Europe, and there was a lot of transitions, and they were trying to think about how to leverage their resources in a data-driven way, because of course the epidemic was changing. And so this was a beautiful paper by a Stanford graduate, Hazma Bastini, and her colleague, she's a professor over at Penn now, that used reinforcement learning to really quickly do this, and it was deployed. So Greece used this for their testing at the border. But perhaps the most famous example recently is ChatGPT. So I think that as many of you might know, natural language processing has had incredible successes over the last decade. And there was a lot of work trying to use transformers to make really, really capable natural language systems. But up to around, I guess like a year and a half ago, most of that work was not known to the broader public. So even though we were getting these amazing advances in natural language processing, it wasn't at the state yet where like everybody was using it. And so the key idea of ChatGPT was to use reinforcement learning to create vastly more capable systems. And I like to talk about ChatGPT not because it's perhaps the most well-known success for reinforcement learning, but also because it exhibits a lot of the different technical challenges and questions that we're going to be covering in this class. So let's just walk through sort of how, at a very high level, sort of this figure from ChatGPT of how the ChatGPT system works in terms of training. So the first thing it does is it does what we would probably call behavior cloning or imitation learning. We'll be covering that in this class. And we'll be talking more about it even in this lecture. So what did it do? So again, just to remind, I suspect everybody in this class probably uses ChatGPT probably multiple times a day, or Claude, or Gemini, or one of the other large language model systems. But just in case you have not, the idea in this case is that you might have some sort of prompt or task you want your language system to do, like explain reinforcement learning to a 6-year-old. And then someone gives a response, like we give treats and punishments to teach, etc. You can try this out with ChatGPT and see how well you think it explains it. And then what that was treated as is sort of a direct supervised learning problem. So just trying to take that input and then to produce that output. And we will call that also imitation learning or behavior cloning in this class. And we'll talk about why. So that was the first step, and this is sort of what people had been doing in natural language processing, and the systems were good, but they weren't that good. So the next idea was to try to explicitly think about utility or rewards, like how good were these particular labels or these particular outputs. So here we're going to actually build a model. We're going to build a model of a reward, which relates to model-based reinforcement learning. And the way we're going to do this is, or the way they did this, is we collect preference data. We ask people to compare or rank across different forms of outputs, and then we use that to learn a preference model. And we're going to cover that in this class. That's going to be one of the differences to this class compared to a couple years ago, that I think preference-based reward signals are really important and very powerful. And so we're going to be covering that in this class this term. So in this case, they would learn a reward, and again, don't worry if you're not familiar with what rewards are and stuff, we'll go through all of that. I just want to give you a high level sort of sense of how ChatGPT is related to some of the things we're going to cover in the class. So they learned a reward signal, and then they did reinforcement learning using that learned reward signal. So now they're going to do reinforcement learning. And this is called RLHF, because it is reinforcement learning from human feedback. And I'll just note here that this was not the first time this idea was introduced. It had been introduced maybe about 4 to 5 years before this for sort of robotics, simulated robotics tasks. But ChatGPT demonstrated that this really made a huge difference in performance. And so I think it's a really nice example of the types of ideas that we're going to be covering, as well as sort of the incredible successes that are possible. Now, for even before ChatGPT came along, there was starting to be a huge interest in reinforcement learning. So some of you, we have an optional textbook for the class. It's by Sutton or Bartow. Richard Sutton is from Canada and is one of the sort of founders of the field. And when I started in reinforcement learning, and I would go give my talks in conferences, it used to be like me and Rich and 30 other people. Nobody cared about reinforcement learning. Except for, a few of us did because we thought it was really amazing. But as you can see, like sort of through like the 2000s, which is when I was getting my training around here, there just weren't that many papers, and the community wasn't nearly as large. But this nice paper by Peter Henderson, the y-axis is papers, shows that there's been this sort of enormous increase in interest. And I think a lot of this was really due to the fact that kind of around here, there was some amazing successes on the Atari video games, where people showed that you could learn directly from pixel input to make decisions. And then there started to be the successes in AlphaGo, and then there became more and more successes. So it is an incredible time for reinforcement learning. This curve has continued to go up. However, I think it's also important to notice that there's also a number of skeptics. So there was a pretty famous talk by Jan LeCun in 2016 at one of the major machine learning conferences, NeurIPS. So Jan LeCun, for those of you who don't know him, is one of the sort of seminal figures in neural network research. He has won the Turing Award. He is an amazing, amazing researcher. So he gave a keynote at NeurIPS. I believe it was a keynote. He certainly gave a very famous talk there, where he was talking about the role of different types of machine learning questions and sub-areas in terms of making progress on machine learning. And he very famously talked about machine learning as a cake. And so he said that the main cake is really unsupervised learning, and that's really going to be the body, the most important aspect of machine learning. Things like representation learning from unlabeled data, that's really going to be the core. And that's where we're going to have huge amounts of data and we're going to make a lot of progress. And then supervised learning was the icing. So that's still pretty important. It's like a very important part of a cake, at least in my opinion. It doesn't have as much, we don't have as much supervised learning, and it's sort of this additional one. And then he argued that reinforcement learning was just the cherry. Now, you know, cherries are important, but not nearly as much perhaps as the rest of the cake. And he went on and talked about some places where he thought that RL still might have a role. But it was considered a really important talk because what he was sort of demonstrating is that reinforcement learning was having a part to play in machine learning, but maybe only a very minor part. Now, I think it'd be interesting to talk to him today. I haven't talked to him recently, so I don't know what his current opinion is. But I think it's a really important thing to think about, like, where are all of these different techniques important, and where will we be able to make the most progress in terms of advancing AI? And so with that, we're going to try and do our first poll, which is about why you guys want to take this class. So we'll look through these. You'll have to bear with us a little bit with, we had a few technical difficulties that we're working with CTL on, but it should work out. So if you go to either the first link in ed, or you go to this HTTP, you can, if you have any issues like, do you want to be registered? If it's hanging, just skip the registration, refresh, that should all sort it out. And then just add in your Sun ID as your screen. And just take a second and write down a bit about why you want to take this class. And it could be anything. It could be that you're really curious about something. It could be because you're doing an internship and they told you you had to take something about reinforcement learning. Any of the things are fine. Just take a minute or two. Thanks for all the great reasons. I will talk about some of those when I talk about also what we're going to cover today and try to address why I think that a lot of the things people are bringing up are things that we're going to be touching upon. So I think if we want to think about, I think it's really important to start thinking about what is reinforcement learning about? Because if we understand what it's about, then we know what sort of types of questions we're interested in this space, and we also understand what sort of applications it might be helpful for. Though, of course, your creativity is unlimited, so you can see what you might come up with other ideas that people may not have thought of for applying RL. But the four things that people typically think about when they think about reinforcement learning as a discipline and as the sort of what reinforcement learning involves is optimization, delayed consequences, exploration, and generalization. So the first is optimization. And the optimization aspect is really just saying that we're thinking about the best way to make decisions, which means that we explicitly have to have some notion of utility. An example of this would be something like finding the minimum distance route between two cities given a network of roads. This means you can directly compare different solutions, because if one solution has a smaller distance than the other, it is strictly preferred. So there are many, many important optimization questions, and reinforcement learning, because it is concerned with making good decisions, cares about us being able to rank or decide across those different ones. The second one is delayed consequences. The idea being that the decisions that we make now can affect things far later. So maybe saving for retirement now has some immediate cost, but leads to some significant benefit later. Or maybe there's something you can do early in a video game that later has a lot of benefit. There are two reasons why delayed consequences is challenging. One is for the reason of planning. Many of you might have actually raised your hand if you've taken AI at Stanford. Okay, so about half of you. So you probably saw planning in AI, and planning is the idea that even when we understand how the world works, it might be really complicated to try to decide what the optimal thing is to do. So you could think of this like chess. All the rules are known. It's still really complicated to think about what's the right thing to do. So when the decisions you make involve reasoning not just about the immediate outcomes, but the longer-term ramifications, these sort of planning problems are even harder. But the other reason this is really hard is when we're learning, meaning that we don't know how the world works, and we're trying to understand how through direct experience. So when we're learning, temporal credit assignment is hard, meaning that if you take some action now and later on you receive a good outcome or a bad outcome, how do you figure out which of your outcomes cause that good or bad later result? But this happens all the time to us as humans, right? How do you know why you got into Stanford? Well, I don't know. Was it because you colored you won a coloring contest when you were 6? Because you scored well on the SAT? Because you went to a good high school? Or you wrote a really good essay? It's really hard to understand this. In some cases, it may be impossible. But when we're getting to make repeated decisions, it's really important that we can start to use the prior experience to figure out which decisions were important or led to good outcomes so that we can repeat them. So that's one of the reasons why this is hard. Exploration is one of my favorite things in terms of reinforcement learning. And the idea of this is that the agent can only learn about the world through direct experience. So it's like trying to learn to ride a bike by trying and failing and trying again, and through that direct experiencing, learning the right way to ride a bike. And the key idea about this is that information is censored in that you only get to learn about what you try. So for example, right now, you don't know how much worse your life would be if you were MIT. I went to MIT for grad school. MIT is also a great place. But you generally can't ever understand what that counterfactual life would have been like. Right? It's one of the central challenges. It's also a huge challenge in causal inference, which is another big interest of mine. It's something my lab works on. So there's this general challenge that you only get to learn about the actual things that you do as an agent, as a human, as an agent, etc. And so the question is, how do you use that experience to figure out how to make good decisions? So as a concrete example of this, you can imagine you're a company and you give some promotion to all your customers. You can't know what it would have been like if you didn't give the promotion to those customers. And even if you can give it to one customer and not another, they are not the same people. So I can't rewind and say, Dilip, who is our head TA, this time I'm not going to give you the promotion. Let's see how that world would have worked out. That's one of the central challenges. So we'll talk a lot about exploration later because it's one of the key things that is different compared to many prior approaches. And generalization has to do with this question of really wanting to solve really big, challenging problems. So we'll talk a lot about what decision policies are, but in general, you can just think of them as a mapping from experience to a decision. And you might think in those cases, you could just pre-program it. So like if your robot goes down the hallway, if it hits the end of the hallway, turn left. But let's think about a video game, which we can think of as just sort of generally having some input image. So let's imagine that it's something like 300 by 400. And let's say we have at least 256 different colors. So now we have an image, set of images that we could see that is at least 256 to the 300 cross 400. So those are at least the space of images, and that's probably an underestimate. And now we get to think about what we would do in each of those different scenarios. So the combinatorics are completely mind-blowing, and we can't write these down in a table. So this is why we would need something like a deep neural network or something else in order for us to try to make decisions in these realistic settings, which are extremely large in terms of the type of scenarios, the number of scenarios we want to make decisions on. So you've probably seen all of these ideas, or at least most of them, in other classes for other types of AI or machine learning. So I think it's useful just to contrast what is reinforcement learning doing compared to these other ones. So the first is AI planning. So in AI planning, generally we're doing some form of optimization, trying to minimize a distance or something like that. We are often trying to handle delayed consequences. And those are the two main things. So we might also have to do generalization if the size of the space is really large. Okay. So that is how, so RL in general will involve all of these. So this is how those would compare. If we think about something like supervised learning does involve learning. So we learn from data, whether something's a cat or not. And we have to do generalization. So we have those two things. And again, this is going to be compared to reinforcement learning, which has all of those. In contrast to supervised learning, where you get the correct labels, and unsupervised learning, we don't get any labels, but we're still learning from experience, and we're still trying to do generalization. Now, the next thing, and this has become a really unpopular thing, is to think about whether we can map reinforcement learning to imitation learning. We talked about this really briefly about ChatGPT, and we'll talk about a lot more in the course. So in imitation learning or behavior cloning or reducing reinforcement learning to supervised learning, we generally assume that we get access to expert trajectories. So this could be like someone saying what they would do in response to those prompts. It could be someone driving a car and then you want to mimic their behavior or some other similar example. So then these ideas is that we get input demonstrations of good policies, and that allows us to reduce reinforcement learning back to supervised learning. So we're sort of taking this and we're reducing it back to here. Now, I think in general, the idea of reductions is incredibly powerful. For those of you that have taken CS theory classes, that's what we do all the time. We reduce things to SAT or other things like that. And in general, I think in computer science, it's one of the strengths of it that they think of how can we reduce one problem to another and then inherit all the progress that's been made on that problem. So in this way, reinforcement learning is similar to other aspects of computer science in that we will try often to reduce reinforcement learning to other problems. This is particularly done in the theoretical aspects of reinforcement learning. Yeah.
Yeah. So just
oh, and whenever you ask, just because I'm going to try and learn names, could you say your name, please?
Yeah, my name's. Yeah. So just to be clear, imitation learning then isn't like a separate technique. It's just an application of supervised learning to like the specific reinforcement learning context.
It's a good question. So I think some of you, there's a lot of techniques that think about when you're doing imitation learning specifically for kind of decision data. You can just think of it just reducing it back. If you want to do imitation learning where you might recover like the reward function, we'll talk more about that soon, and others, then you may need to use other types of techniques as well. But like the most straightforward aspect is just to say, I've got demonstrations, I'm going to ignore sort of like this delayed consequences aspect and exploration, and I'm just going to reduce it back. Yeah, and name first, please.
Wait, what do you mean by input demonstrations of good policy? What does that mean?
Great question. So let me give you an example. So people have thought a lot about this. Maybe one of the first examples of this, or one of the first really public examples of this, was for driving. Like, at least what you could do is I could drive a car. It could record everything that I do in terms of controlling the steering wheel, and then we could, if I'm a good driver, they could say that's a good demonstration. So instead of the car trying to learn from itself how to steer the wheel in order to, say, successfully drive, you could have humans drive it, and it could try to figure out at each point how should I steer the wheel in order to have good behavior. So the idea is that you actually have access already to good demonstrations of what is a good policy. Yeah, name first, please.
What do you exactly mean by optimization here, and why don't SNN work on that?
Optimization and what?
What do you mean by optimization in the table?
Okay, good question. So what I mean is that when we do imitation learning from good trajectories, we are assuming that we want to do well. So we want to actually get a good policy. So imitation learning, we're not normally trying to imitate bad performance, but you could think of this as sort of reinforcement learning, but without the exploration part, because it's not trying to pick its own data.
Why don't supervised learning and unsupervised
Have
have that
the optimization? Yeah, so I think because we normally don't have the notion of utility in those. So you might say this is a cat or it's not a cat. It's not like a good picture of a cat or not. Whereas in decisions, we often have a real valued scalar value of it was a 0.7 good decision. Yeah, name first, please.
We also have the loss function, which we tend to optimize.
Yes, so we do often, we always have loss functions, and that's a great, but where in those cases, there's not normally a utility that goes, so if you could maybe have some smooth notion there of how well do you match a stochastic policy, a stochastic output there. But for many of those, it would be more, if it's did you say it was a cat or not, you would have a binary 0-1 loss. Yeah.
So does that mean if you have the data for imitation learning,
Yep.
it's almost always better than reinforcement learning? So you're kind of avoiding the fast errors, you can directly learn what is good.
Say that again.
So if you have the data for imitation learning,
Yep.
you have someone actually driving the car,
Yep.
does that mean that you'll probably learn a better policy than reinforcement learning, or that's almost always better?
Great question. So we'll get into that. So the question was, if you couldn't hear that, is if you have good demonstrations, say, of driving behavior that you're using imitation learning, can that be better than reinforcement learning? It will depend on your reinforcement learning algorithm. In general, reinforcement learning should always be able to equal or exceed the performance of imitation learning. Yeah.
So, can you explain the difference between IL and RLHF?
Yes, great question. So in imitation learning, what we would have, and this is what was the first part, you would say, people give me, given a prompt, I look on the internet and I assume that those were good. So in the internet, I see if someone said how to explain reinforcement learning to a 6-year-old, this is what they said back. And so I just train on those. What RLHF said is that, well, the internet's a big place, probably not all of it is good answers. So now let's actually ask people which of these two responses they prefer. And now we're going to try to do reinforcement learning on that to actually get to a better policy. Yeah.
I'd like to ask, so AlphaGo actually discovered some Go strategies that are not invented by humans that we have never experienced before. So does it mean that if we apply imitation learning too much, it might actually hinder the model's capabilities to explore what is actually good instead of what humans have thought of, which is probably wrong?
Absolutely. And actually, I think this is on the next slide. Let's go for it. Good. Okay, perfect. So this turns to where are some of the places that you might hope that reinforcement learning would be better than these other strategies. So one of them is where you don't have examples of desired behavior. This is exactly like the example that was just brought up. If you want to go beyond human performance, you cannot rely on human performance just to do imitation learning, because you're not going to be able to go get better than it. So there are a lot of application areas, I think particularly in areas like healthcare or education and others, where we think we can go beyond human performance. And so in those cases, reinforcement learning, because it's trying to optimize performance, could go beyond, it could be a particularly useful technique. And others where you don't have any existing data for a task. So there might be something where you think of it as a decision-making problem, but you don't have prior data. You need to learn from scratch, and you want to directly optimize. And so that's another place where reinforcement learning can be very powerful. Another category is interesting because in some ways it's also kind of a reduction technique. And this is the place where you have an enormous search or optimization problem with delayed outcomes. So there's been a number of examples of the work of doing this from DeepMind, which have been really extremely elegant. So what I put up here is Alpha Tensor. If you haven't heard of it, it's a faster way to do matrix multiplication, which is kind of mind-blowing. So what they did is they said, all right, there's standard ways to do matrix multiplication. This comes up all the time. Could we learn an algorithm that would be better at matrix multiplication? Not me as like a scientist, try to write down an algorithm, have an agent learn one. And they showed yes, and the way they did that was with reinforcement learning. And they've done this in other cases too, like learning faster sorting algorithms. So I think this is a pretty incredible frontier. The idea is saying, could we have AI actually be inventing new algorithms? And one of the ways that they framed it here, and you can think of AlphaGo as similar, is that it was a really, really, really large search problem. And the challenge with really, really large search problems is that even there, we may not have great techniques for solving them. And so it's sort of a reduction. You can think of people taking a planning problem and trying to reduce it to a reinforcement learning problem to make it more tractable. So that's pretty wild. Most of the time we think of sort of RL being reduced in the other direction or involving planning or about that. But here, in some ways, you can think of these as like either adversarial planning problems or expecting max problems that are being reduced back to learning as a way to just more efficiently go through the search space. So those are two of the areas that I think are particularly promising in terms of why reinforcement learning is still a really practical and really important area to think about. I think I saw a question in back, but maybe you.
Yeah, so
oh, what was your name?
For Alpha Tensor, is that like it's faster but within some error of the correct matrix product?
It's faster but with some error?
Or do you actually get the correct value?
No, you get the correct value, which is wild. Yeah. So no, it's just better. Yeah, and one of the really clever things they had to think of in this case was how do you know that the answer is correct? How could you like provably verify that? So it's, incredibly elegant. All right, now we're gonna go quickly through some course logistics before starting to dive into some content, and feel free to interrupt me throughout this or anything else if you have other questions. So in terms of the content, we're gonna start off by talking about Markov decision processes and planning. And then we're going to talk about model-free policy evaluation and model-free control. Don't worry if you don't know what I mean by model, I'll specify it. Then we're going to jump into policy search. Policy search is things like proximal policy optimization and and reinforce and other approaches. Some of you guys might have already seen related ideas, say in robotics if you've taken them. And then I'm highlighting here that this is one of the important differences compared to prior years. So we're going to do a deep dive into offline reinforcement learning. Offline here meaning that we have a fixed amount of data and we want to learn from it to get a good decision policy. And during this, we're going to talk about reinforcement learning from human feedback and direct preference optimization. So that's going to be a new sort of third part of the course that we haven't done assignments on before. So I think that'll be pretty exciting. And we'll also talk about exploration and do advanced topics. So the high-level learning goals of the class is that by the end of the class, you should be able to define the key features of reinforcement learning. You should be able to, given an application, specify how you would write that down as a reinforcement learning problem, as well as whether or not you think it would be good to use RL for it. That you can implement and code common RL algorithms, and that you understand the theoretical and empirical approaches for evaluating the quality of an RL algorithm. So as you could probably imagine from those papers going up, there's going to be continued progress in this field. There's going to be a huge number of different RL algorithms. And so one of the key things that I hope to talk about is sort of how do you evaluate and compare them, which might vary depending on the application area you care about. So the way that the course is structured is that we'll have live lectures, we'll have 3 homeworks, we'll have a midterm, we'll have a multiple choice quiz. We'll do a final project, and then we'll have what I call check or refresh your understanding exercises, which will be going through the poll anywhere. And we'll have problem sessions, which are optional. Problem sessions are a great chance to think more about the conceptual and the theoretical aspects of the class. and they'll be held starting next week. So one of the main application areas I think about a lot is education. I think education is one of the greatest tools we have to try to address poverty and inequality. And so I'm really interested in evidence to think about how do we educate effectively. So with respect to that, I wanted to share this paper that came out, I guess almost a decade ago now, where they did a study to look at how people who are taking massive open online courses, how they spent their time and how that related to their learning outcomes. And what they found is that if you do more activities, there seemed to be a 6 times larger learning benefit compared to watching videos or reading. And you might think this is just based on time, but it wasn't. In fact, it seemed like students spent less time per activity than reading a page. And I bring this up because sometimes I have people who come talk to me right before the midterm and they say, I've rewatched your lectures like 3 times, what else can I do? And while I'm flattered if they want to watch the lectures 3 times, I really highly recommend you don't do that. That instead you spend time doing problems or going through problems from the sessions, going through the homework, going through the check your understandings. It's far more effective and efficient in general. So in general, engaged practice, particularly forced recall, where you have to sort of think about things without checking the answers, is shown to be very effective for learning. And so to achieve the class learning goals, I encourage you to spend as much time as you can, or the time you have available for the course, on those type of sort of directly engaging activities, rather than more passive ones like reading or watching. Yeah. Name first.
Do you have a time frame for when the problem sessions will be held?
Great question. We will announce those by the end of tomorrow. And for those ones that we know it's like impossible to coordinate schedules. So if you can't make it, we encourage you to come in person, but if you can't make it, we also release all the materials and the videos afterwards. I will highlight, I guess, just also on this too, and I saw several people asking about this. Well, let me just go back to this part because it'll allow me to cover. So several people mentioned that they were excited about having some more theoretical aspects. This class does involve theory. It is perhaps, there's probably more theory, I think, probably than the normal machine learning and AI classes, probably a little bit more, and not as much as like an advanced seminar on theory. So normally most problem sets will have like one theory question. And if you're not familiar with some of the sort of theoretical techniques, totally fine. You can come to problem sessions. You don't have to have any prior background in doing proofs to be able to succeed. Another thing people asked about were Monte Carlo tree search. Several people brought up reinforcement learning from human feedback. We will be talking about that. Some people asked about multi-agents. We're going to be thinking about Monte Carlo tree search and other ways to have multiple agents that are making decisions. And a number of people said they wanted to get up to speed on sort of the latest ideas in reinforcement learning so they could read papers or do things in their applications. And I think this was all very relevant to that. The final thing is just we have 5 wonderful TAs who will be supporting. The main ways to get information about the class is to go to the website or go to Ed. We'll be releasing our office hours by the end of tomorrow, and then we'll start them for the rest of the week. And all of you guys are completely capable of succeeding in the course, and we're here to help. Yeah.
Good.
Yeah, thank you.
Going back to the course topic slide.
Yeah.
Do some of those topics include model-based approaches as well?
Yeah, so the first part, great question. So when we first start talking about here, we'll talk about models at the beginning, and particularly when we're defining Markov decision processes. And then we will likely be talking again about them more when we get into the offline approach. There's a lot of really interesting questions about when we're picking different, there's a lot of, we'll get into the fact that there's a lot of different representations you can use for reinforcement learning. And there's a lot of questions over which to use when or when you combine them. And in particular, where do errors propagate in the different types of representations in terms of leading to error in the final decisions you make. But model-based reinforcement learning can certainly be a really powerful tool. Any other questions on the logistics? All right, so let's start to dive into the material. All right, we're going to start with a refresher exercise. So raise your hand if you've seen reinforcement learning at least a little bit in the past. Okay, so most people, not all. If everything I am about to say doesn't make sense, don't worry, we're going to cover it. But I like to kind of get a gauge in case people are like, I've seen all of this before, for the very beginning of the course. So this is going to be a refresher exercise. We're going to do it on Ed. I'll put the link up again, or you can go to Ed. It'll be the second link. So here's the question. We're going to think about how would we formulate a particular problem as a reinforcement learning problem, or as a Markov decision process. So one of the first application areas to use reinforcement learning for education used it in roughly the following way. Not exactly. The idea was that you would have a student that didn't know a set of topics. Let's here just consider addition, which we'll assume is an easier topic for people to learn, and subtraction, which we're going to assume is harder. Imagine the beginning the student doesn't know either of these things. And what the AI tutor agent can do is they can provide practice problems. They can provide subtraction practice problems, or they can provide addition practice problems. And what happens is the AI agent gets a reward of +1 if the student gets the problem right, and they get a -1 if the student gets the problem wrong. And so what I'd like you to think about here is to model it as a decision process. What would like the state space be, the action space, the reward model? If you've taken classes with Markov decision process before and you don't remember, it's totally fine to look up, and refresh your memory. This is not a test. I'd like you to write down sort of, what would a dynamics model represent in this case? And then in particular, what would a policy to optimize the expected discounted sum of rewards do in this case for how I've set up this scenario? So I'd like you to write down your answers, enter them into Ed, and then we're gonna do some small group discussion in about 5 minutes. And if you're not familiar with these particular words like state space, et cetera, it's still fine just to think about, given what I've told you about the reward for an agent, what might happen in this case. Okay, sorry, you might have to switch to the Ed. All right, try to enter in something that's okay if you're not sure, and then turn to someone near you and compare what you did. All right, we're going to come back. Hopefully, I heard a lot of really fruitful discussions. So let's see. I know at least one group I talked to had a great idea for what the state space could be. Do you guys want to share what your state space was, and maybe tell your name as well?
Oh, sure. We said the state space could be just like a set of word pairs of like two like natural numbers or any kind of numbers of like how good the student is at addition and how good the student is at subtraction.
Yeah, so you could imagine something which is at addition and subtraction. So you could imagine something like this, where you just have like a vector pair, where it's like maybe they're 0.9 close to mastery for addition and like 0.4 close to mastery for subtraction. This is not the only way you could write down. There's lots of choices for the state space, but that would certainly be one reasonable one. Those are challenging in some ways because you can't directly observe them, but it's a pretty natural way to write it down. And in fact, there are commercial systems that essentially do that, where they have like, for those of you familiar with hidden Markov models, it's basically a hidden Markov model over whether someone has mastered something or not. Didn't we have a different type of state space that they wrote down? Yeah.
Ben and I talked about, we basically want to encapsulate.
Oh, could you say your name first, please?
The knowledge that the student has, and also maybe the questions that have already been asked, to like capture the environment, the current environment that we're at. So we all, like, I guess this is a better representation of capturing the knowledge the student has. We were thinking of also just like the history of questions and the students' answers, whether they got it right or not. I guess that's harder to represent mathematically.
No, that's beautiful. So exactly what was that right? Yeah, that's exactly what. So that was the other one I was hoping people might come up with, which is the idea of this just being a history, like a history of all the previous questions you've given, or all the questions the robot has given the person and what they've responded. So you could imagine it's like observation, question, reward, ... And in fact, those two representations here, the history and how the student, how good the student is, can be, depending on your representation, be exactly isomorphic. So sometimes this can be a sufficient statistic to capture that history. And as Aaron was pointing out, one of the challenges with histories is that they grow unboundedly. So if you want to have like your neural network be predicting something, you might be able to use something like an LSTM, or you might want to summarize the state. So those are both great ideas for what the states could be. There's not a right answer. Both of them would be great, but there's also other ones. The actions, I heard many people share what the actions are. Someone want to tell me what they are in there? I know you guys mentioned what the action space was.
Sure, just whether it goes in addition or subtraction.
Exactly. So these are just like what the agent can actually do, the teaching agent. Addition question or subtraction. And the reward model is +1 if the student gets it right. I saw some questions about what a dynamics model is, and inside of the responses people were putting on the form. What I mean by a dynamics model here, and we'll talk a lot more about this, is what happens to the state of the student after a question is given. So in this case, and I talked to some people about this who had a great understanding of this already, the idea would be sort of how does either that history change after you give a question to the student, or how does the sort of internal knowledge of the student change? So the hope would be, as long as this sort of curriculum is vaguely reasonable, that after you give the student an addition question, they now know more about addition, or they're more likely to have mastered addition. So that would be sort of this idea of there being a dynamics process that where you start in one state, you get an action, and now you transition to a new state afterwards. And we'll talk a lot more about that. Now, what is the challenge with this particular representation? Yeah, can you say your name first, please?
Depending on your implementation, there's a risk that the agent just gives really easy problems.
Yeah, in fact, it's exactly right, and in fact, that's exactly what we think will happen. So we think that an agent that is maximizing its reward should only give easy questions. So in this paper, which I took the inspiration from for this example, it was very close to this. So they tried to pick not correctness, but how long it took people to do problems. And so if the student took less time to do problems, which isn't necessarily bad in itself, it might indicate some notion of fluency, the agent got more reward. But of course, what that means is that you should just give really easy questions that will take the student no time to do, because then the agent can get lots and lots and lots of reward. And this is probably not what the the designers of this system to try to help students learn things intended. They probably actually wanted the students to learn both addition and subtraction. But I bring this up because this is an example of what is often called reward hacking, where the reward that we specify does not necessarily provide the behavior that we really hope to achieve. And we will talk a lot more about this. In this case, it's a fairly simple example where we can see it fairly quickly. But there are a lot of cases where it's a lot more subtle to understand whether or not the system really will do what you hope it will do. And we'll talk about that more throughout the course. All right, great. So we're going to now just start to talk about sort of sequential decision making more broadly, and some of this will be a review for some of you, but I think it's useful to go through and refresh our memories. So the idea in sequential decision making under uncertainty is that we're going to have an agent that is taking decisions or actions, so I'm going to use actions and decisions interchangeably, which are going to interact in the world, and then they're going to get back some sort of observation and reward signal. So in the first example I just gave you, it's like the agent provides a problem to the student, and then they see whether the student gets that correctly or incorrect. And then they also use that information to get a reward. So they're sort of getting reward and feedback. And the goal in this case is for the agent to select actions to maximize the total expected future reward, meaning both the immediate reward they get now as well as the rewards they're going to get over time. And this generally is often going to involve balancing long-term and short-term rewards. So there are lots and lots of examples. I'll just go through a couple of them just to give you a sense. So one is something like web advertising. In this case, Amazon, for example, might choose like a web ad to show you or a product to suggest to you. They might observe things like view time and whether or not you click on the ad, whether or not you make a purchase. And the goal in this case could probably be for them to optimize either click time or view time or revenue. In the context of something like robotics, the control space or the decision space might be something like how to move a joint. And then the feedback that the robot might get back might be something like a camera image of a kitchen, and perhaps they just get a +1 if there are no more dishes on the counter. Now, just a quick question, could this potentially be a reward hacked specification? I see some smiles. What could happen? Yeah, keep saying your question.
The robot could just push everything off the counter.
Which I will say, it's tempting, right? You're like, I'm just going to make it all go away. But in fact, it does not solve the problem. And now you just have broken dishes and food on the floor. So that would not be a good thing to do. So yeah, this would be probably not a great reward to put. You probably want to reward more like that the dishes are inside of the dishwasher and finally clean. So not just that they were put in there, but actually that you ran the dishwasher. So this would be a second example of a setting. Another would be something like blood pressure control, where you could imagine that the agent gives recommendations like exercise or medication. The feedback is things like blood pressure, and then you would define some reward, like maybe +1 if you're in a healthy range, else some sort of sloping penalty for being outside of the healthy range. All right, so all of these are nice examples of the numerous ways where we often try to make sequences of decisions under uncertainty. In general, we're going to assume that we have a finite series of time steps. So we're not going to be thinking about continuous time in this class. Lots of interesting things there. We're not going to cover it. What we're going to assume is that the agent is making a series of decisions. So we're going to think of there being a series of time steps, like 1 minute, 2 minute, 3 minute, 4 minute. The agent will take an action. The world will update given that action and emit an observation and a reward. And then the agent receives that, updates, and then makes another decision. We just close this loop. It's a feedback cycle. In this case, as we sort of just talked about at a high level, we can think of there being histories, which is sequences of past actions, rewards, and observations up to the present time point. So the history HT would consist of all the previous actions of the agent, the observations it receives, and the reward it's got. In general, this is something you could use to make decisions. You could just keep track of everything you've experienced so far and then condition on that to try to make your next decision. But we often are going to assume that there's some sort of sufficient statistic that we can use to summarize the history. It will be much more practical in many cases. Yeah?
Oh, sorry, just to make sure, is observation just basically like the history, it's like a previous history of the...
Okay, and what's your name? So the observation in this case would be something like the immediate information you get back after the last action. So in the case of the student, it would have been whether they get the last problem correct or not. So just like a single time step. And then the history would be everything, like up to this time point. Good question. Okay. So in particular, often to make things tractable, and because often in reality it's not a terrible assumption, we're going to normally make the Markov assumption. And the idea is that we're going to try to come up with some sort of informative information state that is a sufficient statistic of the history. So we don't have to keep around all of the prior history of everything the agent's ever done or seen or gotten reward for. And what we say is a state ST is Markov if and only if the probability of going to the next state, given the current state in action, is the same as if you'd conditioned on the whole entire history. So another way to say this, which I think is kind of a nice evocative idea, this is not from me, it's from others, is that the future is independent of the past given the present. That means if you have a rich representation of your current state, you don't have to think about the previous history. And of course, in general, this will be true if you make S equal to HT. But in general, we're going to be thinking often of sort of projecting down to a much smaller state space. So for example, you might say, well, I could think about someone's blood pressure from all of time, but maybe it's sufficient just to think of their blood pressure over the last 2 hours in order to make my next decision. Yeah.
Is there a difference between state and observation in this case?
Great question. Yes, in general. So I'll give you a particular example. Atari, which is these video games that DeepMind learned an agent to play, what their state in that case was the last 4 frames. So not just the last frame, the last 4 frames. Does anybody have an idea why you might want 4 frames instead of 1? Yeah.
Maybe like, so you can see like if there's momentum to an object already moving.
Exactly. It gives you velocity and acceleration. Yeah. So there are a number of cases where you might think that there are parts of the state that really depend on temporal differences, and then in those cases you're going to want more than just the immediate state. Great questions. All right, so why is this popular? It's used all the time. It's simple, it can often be satisfied, as we were just discussing, if you use some history as part of the state. Generally, there are many cases where you can just use the most recent state. Not always, but many cases. And it has huge implications for computational complexity, data required, and the resulting performance. What I mean by the resulting performance is that in many of these cases, just like in a lot of statistics and machine learning, there will be trade-offs between bias and variance. And so there'll be a trade-off between using states that are really small and easy for us to work with, but aren't really able to capture the complexity of the world and the applications we care about, so that it might be fast to learn with those sort of representations, but ultimately performance is poor. So there'll often be trade-offs with how we actually, the expressive power of our representations versus how long it takes us to learn. Right. So one of the big questions when we talk about sequential decision-making processes is the state Markov? And is the world partially observable? So
My question is that doesn't the Markov assumption make this reward attribution problem somehow harder?
Why is it hard? Good question. Well, I don't know. I guess you could imagine it might make it easier or harder. There's still the question of you might only get periodic rewards, and you still would have to figure out which decisions caused you to get to a state where you got those rewards. Yeah, so let me think of it. So you might have a case where the reward might be a function of your current state. Let me think if I can think of a good example. Okay, so let's say maybe you want to run a marathon, and you get a plus 100 if you make it. Boston Marathon is a competitive marathon to get into, so you get a plus 100 if you can qualify for Boston. And you do a lot of different things in your training regime. You eat healthy, and you sleep, and you train, and then and you get 0 reward for any of that. And then on the day of your race, you see if you qualify for Boston. So your state only, your reward for getting into Boston only depends on that current state, but you don't know which of those decisions, was it that you ate well, was it that you slept, was it that you trained every week for 17 weeks, caused you to get to the state in which you qualified for Boston. And so that's independent of the Markov assumption in that case, because you still have the question of what series of decisions allowed you to get to a state that achieved high reward. Great question. So another thing is whether the world is partially observable. We will mostly not be talking about this in this class. Michael Kockendorfer has a great class where he talks about this a lot. But this does relate to the case we talked about with students. So for students, one way you could think about that is that there's some latent state that you can't directly access, which is whether or not they know addition or they know subtraction. But you get noisy observations when they do problems where they get it right or get it wrong. And the reason it's noisy is because, all of us make mistakes on addition sometimes, whereas I have complete faith that everyone here actually knows how to do addition. And sometimes you might guess right, even if you don't know it. So the idea is that it's latent. You don't directly get to observe it. This comes up in a lot of robotics problems too. So I'll just give a quick example here. If you have a robot that uses a laser rangefinder to figure out these little arrows or lasers to figure out its environment, so it could have 180 degrees of laser rangefinders, and what it's getting back is just the distance in all of these different angles to where it hits a wall. So as you can imagine, many rooms would look identical. So any room that has kind of the same dimensions would look identical to that robot, and it wouldn't be able to tell is it on the 3rd floor or the 2nd floor. So that would be a partially observable case where it can't uniquely identify its state based on its observations. So we won't talk too much about that, but it's important to know about. Another thing is whether the dynamics are deterministic or stochastic. So there are many cases where things are close to deterministic, like if I put down a piece on a Go board, it goes there. But there are other things that we often treat as stochastic, like when I flip a coin, I don't know whether it's going to be heads or tails. So that'll be an important decision. And then the final thing is whether the actions influence only immediate reward or reward in next state. So as an example of this, you might imagine if you were making a policy for what ad to show to people, and you just imagine for each person coming onto the web, you just show them, like onto your website, you show an ad and then they go away and they either buy something or they don't. A bandit would be a case where like you just have, bless you, you have a series of customers coming in. And so whether or not I show a particular ad and he clicks on it or not does not impact whether or not Ellen comes along and likes an ad. So that's a case where it impacts your immediate reward, but not the next state. We can talk more about that. All right, let's think about a particular sort of running example. We'll think of a Mars rover. So Mars rover is a Markov decision process. Imagine that Mars is really small. We only have 7 places in Mars. So in this case, we would have the state is the location of the rover, which is one of 7 discrete locations. We could have actions called try left and try right, meaning that our rover is not perfect. So sometimes it tries go a direction and it doesn't succeed. And let's imagine that we have rewards, which is there's some interesting field sites. And so if you spend time over here, you get a +1, and you have spent over here, you get a +10, and else you get 0 reward. So this would be a particular case where we could think of there being these states and these actions and rewards. So when we think of a Markov decision process, we think of there being a dynamics and a reward model. So in particular, the dynamics model is going to tell us how the state evolves as we make decisions. We will not always have direct access to this, but the idea is that in the world, there is some dynamics process and things are changing as we make decisions. So in particular, we generally want to allow for stochastic systems, meaning that given we're currently in a state and we take a particular action, what is the distribution over next states that we might reach? So for example, I'm that Mars rover and I'm going to try to go to the right. It might be that I can go to the right with like 50% probability, but I'm not a very accurate rover, and so 50% of the time I go to the left, or maybe I stay in the same location. So this dynamics model just specifies what actually the distribution of outcomes that can happen in the world when I make a decision. The reward model predicts the immediate reward, which is if I'm in this state and I take this action, what is my expected reward? I want to highlight here that there are different conventions. You could have the reward be a function only of the current state. Excuse me. It could be a function of the state and the action you take, or it could be a function of the state, the action you take, and the next state you reach. You'll see all of these conventions in reinforcement learning papers. Probably the most common one is this, but we'll try just to be specific whenever we're using it so it's clear. And you can always ask me or ask any of the TAs if it's not clear. Bless you. So let's think about sort of what a stochastic Mars rover model would be. So I've written down a particular choice for the reward. And let's imagine that part of the dynamics model is the following, which is if I start in state S1 and I try to go to the right, then I have some probability of going to S2, else I have some probability of staying here. What I want to be clear about here, and this relates to the question before about models, is that this is like the agent's idea of how the world works. It doesn't have to be how the world actually works. So what I told you in the previous slides is that imagine that in this world, in reality, this gives you +1 and this gives you +10 in terms of the reward. That's how the world actually works. But the agent might have the wrong model of how the world works because it only learns about the world through its experiences. Or it just might have a bad model. So this is an example of sort of like a model-based Markov system where the agent would have a particular representation of the dynamics model and a particular assumption over how the rewards work. In these settings, we have a policy. A decision policy is just going to be a mapping from states to actions. It's like an if-then table. If it's deterministic, we just have a single action that we would take in a particular state. Like maybe we always show this one ad to a particular customer. Or we could have a stochastic policy where we randomize this. And so this would be something like, oh, when this customer shows up, I show, a vacation ad or I show a board game ad with, 90% probability versus 10%. Both types of policies are really common, and it can depend in part what sort of domain you're in and whether you're trying to learn from that experience. Okay, so let's see what that would look like in this case. So for Mars rover, you could say that no matter where it is, it always just tries to go right. So that would just be one example of a policy you could have. And it just requires you to specify for every single state what is the action you would take or what is the distribution over actions you would take. So in this sort of setting, we're normally interested in two main, oh yeah.
Yeah, question. So it's like making like decisions based on the state that it's in. Can it like learn to like switch from like different all types of policies, so not just like different actions based on the state, but also switch to like checking the past state, the future state, in the same way like in deep learning it like tries a bunch of different functions. Can it do that or can it not do that?
Great. Was it, remember your name? Yeah, so great question. It will in general when we're learning, it'll change its policy a lot over time. So it might start with a particular policy, and then over time it will explore lots of different policies in trying to search for something that's good. That's a great question, and that relates to what I was just putting here, which is two of the central questions we're going to talk a lot about, particularly at the beginning, is evaluation and control. Evaluation says someone gives you a fixed policy, and you want to know how good it is. Like maybe your boss says, hey, I think this is the right way to advertise to customers, and we're going to make a lot of money. And you go out and you just deploy that particular decision policy, and you see how much money you make. So that would be evaluation. Control is you actually want to find the best policy. And so in general, to actually find the best policy, we're going to have to do a lot of trial and error, and we want to do that in a strategic, efficient way so we can quickly learn what that good policy is. So in general, we're going to be talking about things I just want to highlight. We're going to sort of build up in complexity in terms of the type of problems we're talking about. So we're going to be thinking about both like planning and control and sort of thinking about how complicated these spaces are. Okay. So we're going to think about evaluation and control, because evaluation is often a subpart of doing control. If you know how good a policy is, you may be able to improve it. And then we're going to talk about tabular and function approximation methods, because we're going to want to be able to solve really large problems. And then we're going to talk about both planning and learning. In planning, we're going to assume someone gives us that dynamics model and that reward model and the state and action space, and we're just going to try to find a really good policy. And in learning, we're going to actually have to control the decisions we make to give us information that allows us to identify an optimal policy. Okay. All right. So what we're going to start with is sort of the simplest of the settings, which we're going to assume that we have a finite set of states and actions. We're given models of the world, meaning someone like writes down for us what those look like. And we want to evaluate the performance of the best decision policy. And then compute the optimal policy. And we can think of this really as AI planning. Okay. So to think about how this works, we're going to start with Markov processes and then build up to MDPs. And this is relevant because it turns out you can think of evaluation as basically being a Markov reward process. Okay, so how does a Markov chain work? And just raise your hand if you've seen Markov chains before. Awesome, okay, so most people have, which is great. So this is a memoryless random process. There's no rewards yet. There's a finite set of states in this case, and we have a dynamics model. And if it's just a finite set of states, we can just write this down as a matrix. Says what's the probability of going to the next state given the previous state. And so you could just have this say in our, this would be a Markov chain transition matrix for our Mars rover case. Okay. And if you wanted to get an episode, you just sample. So let's say you always touch down in state S4, you could just sample episodes from that particular chain. Yeah?
In P, do all rows and columns need to add to 1?
All of the, what's your name? Yeah, so all of the rows have to sum to 1.
Okay. Then is it coincidence that columns sum to 1?
Yeah.
Okay.
Yeah. I was thinking just now that I should have changed that. Good question. Yeah. Because then, and we'll see also why that's important later. Okay, in a Markov reward process, it's a Markov chain plus rewards. So same as before, but now we have a reward function that tells us how good each of those states are. Okay, and we're also going to have a discount factor, and I'll talk about that in a second. We still have no actions, and we can express R as a vector. So in this, we could imagine our Markov reward process where we have a +1 in S1, 10 in S7, so +1, and 0 in all other states. In this case, this is where we start to see the ideas that are going to be really useful for decision processes, which is we can start to think about how good particular trajectories are. So we're going to have a horizon, and you're going to see this in your homework too, which is the number of time steps in each episode. It could be infinite, or it could be finite. It's like basically how many time steps do you get to make decisions. And the return, which we're going to call GT, is just going to be the discounted sum of rewards from the current time step till the end of the horizon. And a value function in this case is just going to be the expected return. In general, this is not going to be the same as the actual return unless you just have a deterministic process. Because the idea is that you're going to have stochasticity in the trajectories you reach, and because of that, you're going to get different rewards. Right. So you might wonder, particularly if you haven't seen it before, why do we have this discount factor thing? So we're sort of weighing earlier rewards more than later rewards. Well, one is that it's just mathematically really convenient. It's going to help us not sum to infinity, particularly if we have infinite number of time steps we can make decisions. And it turns out humans often act as if there is a discount factor. Like often we sort of implicitly weigh future rewards less than immediate rewards. And this is true for organizations too. And if the episode lengths are always finite, you can always, bless you, use gamma equal 1, meaning you don't have to make a large discount. But when you have infinite horizons, it's generally important to make this less than 1 so your rewards don't blow up. Part of that is because it's really hard to compare infinities. So it's hard to say like this policy that has infinite reward is better than this other policy that has infinite reward. Whereas you can keep everything bounded if you have a gamma less than 1. All right. Next time, we will start to talk about how we actually can compute the value of these types of Markov reward processes and then start to connect it to decision processes. I'll see you on Wednesday. Thanks.